Hi there, welcome back. In this slice of physics, we're going to discuss everything about uniform motion. As you will remember, uniform motion in physics is simply motion with a constant velocity. The example I like to give is this is as if you're in cruise control on a perfectly straight road, so your speed is not changing and your direction is not changing. Those are the two conditions required to keep a constant velocity. We're going to first look at position time and velocity time graphs and see what they look like for a uniform motion. And then we will see how we can extract information for the motion from these graphs, which will lead us to the equations of uniform motion, which you will later use to solve uniform motion problems. So let's get started with an example of a position time graph for uniform motion. So I've got position here, let's say along the x-axis, and let's say that's in units of meters, and I've got time on the x-axis in units of seconds. So what does a position time graph for uniform motion look like? Well, it's got to be a straight line. The position has to change in a very uniform manner, so it has to be a straight line. It could be one with a positive slope, as I've shown here. It could be one with a negative slope. Technically, it could also be one with zero slope, although if you remember, zero slope is horizontal, where the position is not changing. So even though you could call it uniform motion with zero velocity, it's really that the object is at rest at one position and not moving at all. Okay, so let's come back to this example. We also discussed that the slope in a position time graph is nothing but the velocity. And let's take this geometrically and see what that turns out to be. So I'm going to take two times here. Let's call this time t1, and this time here I'm going to call it t2. And the corresponding positions are at t1 I've got position x1, and at time t2 I've got position x2. Now let's investigate the slope between these 2 points t1 and t2. Well, the slope is nothing but the rise over the run, and so in this case my rise, the amount that this graph increases in the vertical direction, is here. So I've got rise there, and the run is simply how long it spans in the horizontal direction, so that's my run. So in terms of these variables x1, x2, t1, and t2, let's see what the slope ends up being. So we got slope is rise over run, and the rise is this little piece over here, which is nothing but this entire vertical length, which is the same as x2, minus this vertical length, x1. So if I subtract x1 from x2, I get my rise. So that's simply x2 minus x1. And then the run similarly is nothing but this entire horizontal length, which is t2 minus t1. That'll give me the run. So I've got t2 minus t1 in the denominator. So x2 minus x1 is just, in English, I can say that it is the change in the x position, and t2 minus t1 is the corresponding change in the time, which is the time duration. And change in physics is written with this capital letter delta. So x2 minus x1 can be written as delta x, and t2 minus t1 can be written as delta t. And since we said the slope in a position time graph is nothing but velocity, this whole thing here is nothing but vx, the velocity in the x direction. So by starting with the concepts of a position time graph for a uniform motion, we have come up with the first equation of uniform motion, which is simply that the velocity along the x direction is the change in position along the x direction divided by the time duration that change takes. And the velocity along y direction would similarly be the change in the y position divided by the corresponding time duration, and so on. And by the way, if I want to remind myself that velocity and displacement are vectors, I can draw these arrows here to show that they are vectors. And by simply rearranging this, I can multiply both sides of this equation by delta t, and that rearranges to give me displacement in terms of velocity and the time duration. So this is not necessarily a new equation, but another form of the same equation that is more useful in solving some problems where you know velocity and the time duration and you want displacement. Now in our example, we used the points that we investigated. We called them 1 and 2. It's common to call these points as the initial and the final state of the motion. So if we did that, this delta x would simply be xf minus xi. And that would be equal to vx times delta t. And positions are also vectors with respect to the origin of the coordinate system. So when I rearrange this by adding xi to both sides, I get xf, which is a final position, equals xi plus vx times delta t. So here are my three common equations of uniform motion. So those are our equations of uniform motion, but let's come back to the graph and see what the corresponding velocity time graph for this motion would look like. So we got the y-axis now set up for velocity in meters per second. The x-axis, as before, is still for time. The velocity of this motion is the constant everywhere. The slope of a straight line does not change, so you've got a constant velocity, which is what, by the way, made it a uniform motion. Moreover, the velocity in this case is positive. This is a positive slope rising as it's moving to the right. So the velocity plot will be above the x-axis. So it would look something like this, a flat horizontal line with a constant velocity value above the y-axis. And we called this velocity for this example Vx. So let me label that there. And now let's say we're interested in figuring out what this area under the velocity time curve will be between these two times, t1 and t2. So we're interested in determining this area over here. Since it's a rectangle, the area of the rectangle is simply the height times its base. So the area under the velocity time graph would be the height, which is Vx, times the base, which as before is t2 minus t1 or delta t. And that Vx times delta t is nothing but the displacement. So this leads us to another key tie-in between equations and graphs, is that the area under the velocity time graph is simply the displacement. And as we discussed before, areas above the x-axis would be positive. So in this case, this displacement is going to be a positive displacement because my velocity is positive and my delta t is always positive, so displacement would be positive, which corresponds to an increasing position as time ticks. So in this slice of physics, we looked at uniform or constant velocity motion. Specifically, we studied the position time and velocity time graphs for this motion and tied them into the equations of uniform motion. Thanks for watching.